Okay, so I'm sorry about that, guys, out there in Zoom. I was just saying to the group here in the classroom that if you review your assignments, exams, and also the past exams that I have posted online, then that should serve you well in terms of doing your best in your upcoming final exam. And I also said that the exam will be 8 questions, so there'll be a question per chapter, right? So that's basically the setup. And we'll be using a full class period for that final exam. All right, so, and I was saying, if there are questions you guys have, I'm more than willing to answer them now, so that's what I was waiting for.
Assignment number 1, question 6.
Assignment number 1. Number 6.
Yes.
Okay, so this question says a solution is prepared from 96.0 grams of a non-volatile, non-dissociating solute in 5.25 moles of toluene and has a vapor pressure of 0.161 atmosphere. What is the molecular weight of the solute? And the vapor pressure of the pure toluene is given at 60 degrees, which is 0.184 atmospheres, all right? So basically, this is a Raoult's law type of problem. Let me turn on my thing here. Okay, so basically, Raoult's law says that the vapor pressure of a solvent would be equal to the mole fraction of that solvent times the vapor pressure of that pure solvent, right? So that's the equation we're going to use. Now, they gave you this, which is the 0.184, and they gave you the vapor pressure of the solvent, which is 0.16 atmospheres. So we can rearrange this to get the mole fraction, which is PA over PA0. So that will be equal to 0.161 atmospheres divided by 0.184 atmospheres. And let me do that calculation. So that's 0.161 divided by 0.184. So according to my calculation, this works out to be equal to 0.875. All right? So that's a mole fraction of the solvent in this particular solution. Now, what the question is asking for is the molecular weight, right? Now, another thing I should mention too is that by definition, the mole fraction of A would be equal to the number of moles of A present in the mixture plus the number of moles of A plus the number of moles of the other substance, which is what you're trying to find. I'm going to call it B, number of moles of B, right? And we already know that that is equal to 0.875, right? So what I would do here, because the question is asking for the molecular weight, recall that the molecular weight and the molar mass are both numerically the same, right? So basically, if you find the molar mass of the substance, then all you have to do is switch the units and that would give you the molecular weight, right? So basically, our aim is to find this right here, right? Now, they gave us the number of moles of the toluene, which is Na. So basically, this is going to involve some algebraic rearrangement. So I'm going to do this. I'm going to cross multiply to get Na is equal to Na plus Nb times 0.875. And then what I would do is distribute. So you're going to get Na is equal to 0.875 times Na plus 0.875 times Nb. And then to isolate NB now, what I would do is subtract 0.87575 Na from both sides, right? So that this will go with that. You're going to end up with Na minus 0.875 Na, and that will be equal to 0.875 NB. All right? And then now to get NB by itself, NB would be equal to Na minus 0.875 Na divided by 0.875. So for the numerator part, it was going to be 1 minus 0.875. So that works out to be equal to 0.125 Na divided by 0.875. Which works out to be 0.143 Na. So we have the relationship between NB and Na. And Na is given as 5.25. So 0.143 times 5.25 moles. And let's see what that gives, 0.143 times 5.25. So according to my calculation, this works out to be 0.751 moles, right? So that's the number of moles of the solute. But the question is asking for the molecular weight of the solute. So the next step would be to divide the mass of the solute by the number of moles, and that will give us the molar mass. So here I'm going to say that the molar mass is equal to the mass in grams, which is the 96.0 grams, divided by the moles, which is 0.751 moles. And let's see what that gives. 96 divided by 0.751. So according to my calculation, this would have to be rounded off to, hold on, let me make sure the sig figs is right here. Okay, so based on what I see here, this would be 128 grams per mole, right? Which means that the molecular weight is equal to 128 AMU, which is what the question is asking for. And that's how that is done. All right? Any questions about this? Any questions? Yes, sir. Oh, yeah. Maybe not this exact question, but colligative properties generally. Yep. And this is a colligative property. This is the first chapter that we did. All right. Any other questions? Or any other questions about this, or any other questions, Pierre?
Professor?
Yes, sir.
For question number 5, it's the question right before that one. It says for glucose, we do not find the molecular fraction because it was the vapor pressure was 0, correct?
All right, hold on 1 minute. Let me clear this first and scroll back up to that question. See what you're talking about. Okay, so it says if I add 45 grams of glucose to 500 grams of water, what is the vapor pressure of the solution? So what are you asking?
So for glucose, we ended up getting a total of 0 when you multiply the vapor pressure times the molecular fraction.
Okay.
I was wondering, is it because the vapor pressure of glucose is always going to be 0 because it's a solid?
Exactly. For most solids, the vapor pressure will be 0. I think, if I remember correctly, when I was answering this question, I said that the total vapor pressure would be equal to the mole fraction of, I'm going to use G for glucose here, times the vapor pressure of pure glucose plus the the mole fraction of water times the vapor pressure of pure water, right? And the point that I made, which I think is what you're referring to, is the fact that the vapor pressure of pure glucose is zero because it's a solid, right? So that simplifies things. That means that all of this here would be equal to zero. So this simplifies to the vapor pressure, the mole fraction of water, the mole fraction of water times the vapor pressure of water, pure, would be equal to the total vapor pressure of the mixture. And then we go ahead and solve the problem, which requires for us to find the mole fraction of water. And we can find that because we're given the mass of glucose, and the mass of water. We'd have to convert each of these to moles. And then find a mole fraction based on those mole values. And that would go here, multiplied by the vapor pressure of pure water, which is given here. And that's how we get the total vapor pressure. But to answer your question, as you said before, when it comes to solids, yes, you can assume that the vapor pressure is equal to zero. Now, if you have a mixture of two liquids, then you can't make that assumption. You have to take into account the vapor pressure of both liquids, because both liquids can produce vapors and therefore can exert vapor pressures. All right?
Thank you.
Oh, I'm sorry, yes?
Yeah, I was just saying thank you.
All right. Any other questions? Yes, ma'am.
4 on the practice test.
Question 4 on the practice test. You talking about the final or just
The final.
All right, so let me go. Excuse me. So I think that's located here, right? And okay, so what question now? 4. Okay, so this is 4. Question is asking for you to calculate the pH of the following solutions, and the first one is 0.36 m sodium acetate. That's what this is, right? So again, in terms of solving the problem, the formula itself is not important, right? So I'm just using A minus to represent the conjugate base, because what's going to happen is that hold on. The sodium acetate is going to undergo dissociation, right? So NaA will undergo dissociation to form Na plus A minus. And that dissociation is going to be complete. And remember, I think I mentioned this, if not the last class, the class before. Sodium salts, potassium salts, lithium salts, they will all dissociate completely, right? So you can assume complete dissociation. Because of that complete dissociation, whatever the molarity of this is, the molarity of this ultimately is going to be the same, right? Because of the 1-to-1 ratio. So therefore, this A minus now is going to interact with water as a base. In other words, the A minus is going to take a proton from the water to form HA and OH minus. So, and that would be a weak base, so therefore you're going to have that back and forth. You're going to have an equilibrium system set up. So the A minus concentration initially would be the same as this right here, which is 0.36, right? Initially, you're going to have no HA or OH minus, and then the change here would be that for the A minus, is going to be minus X as the system approaches equilibrium. The change here would be plus X and plus X. So at equilibrium, you're going to have 0.36 minus X here for HA and OH minus. So because it's a base, we can write down the equilibrium expression for a base for this system. So Kb is equal to the concentration of HA and OH minus multiplied to each other divided by the concentration of A minus at that juncture, right? So scroll down here. So basically, because the concentration, let me clear this here. Because the concentrations of the HA and OH minus are the same. When you multiply them, you're going to end up with X squared up top as the numerator. And then down here, you're going to have 0.36 minus X down here as the denominator. And we're going to set that equal to KB. Now, here's the thing. If you consult any, like the table that you'll have access to during your exam, if you consult that table, you'll not see a KB value for the acetate ion, but you will see a Ka value for acetic acid. So basically, we have to use this relationship right here to determine Kb, right? Remember, Ka times Kb is equal to what? Kw, right? So we can find Kb by dividing Kw by Ka, right? So you're going to end up with Kb equal to Kw divided by Ka. And that's exactly what I did right here. Kw is 1.00 times 10 to the minus 14. Ka is, and of course you can look that up in the tables, and you'll see it's going to be 1.8 times 10 to the minus 5. So basically, it turns out that Kb is equal to 5.6 times 10 to the minus 19, 10 to the minus 10. And then we assume that X is much less than 0.36, which simplifies this equation here, and therefore we can solve for X. And when we do that, there it is here. When we do that, we end up with X being equal to 1.4 times 10 to the minus 5. Of course, you have to check to make sure that your assumption is valid. How do we do that? We determine the percent dissociation, right? So we take the 1.4 times 10 to the minus 5, which is the concentration of OH minus, divided by the initial concentration of the A minus, and we see that this is less than 5%, 3.9 times 10 to the minus 3. So basically, we can go ahead and use the concentration of OH minus equals to 1.4 times 10 to the minus 5. And then we find the POH, which is minus log of 1.4 times 10 to the minus 5. And then based on that value, we can easily find the pH, which would be 14.00 minus the POH. And that's how we get the 9.15 right here as the answer. All right. So that's basically how that is done. For the B part, in this case, again, ammonium chloride, just as in the case of sodium acetate above, will undergo complete dissociation. And we know that because the ammonium, well, most chlorides are soluble in water anyway. So the ammonium chloride will undergo complete dissociation to form NH4 plus Cl minus. Let me just say this. I don't think I've had any of you in my Chem 1 class, but in my Chem 1 class, there's a table which is still available, which gives you, what do you call it, solubility rules. I don't know if you guys are familiar with the solubility rules for ionic compounds. You can use it to determine what type of ionic compounds will dissolve in water. Where is it? Okay, I thought I had it here. Oh, no, it's in, okay, I know where it is. I think it's almost the last page, if not the last page. Okay, so this is it right here, right? This is used to make predictions as to what type of, what ionic compounds are soluble or insoluble in water, right? So for example, I said earlier that group 1A metal salts, like potassium, sodium, and so on, they're always soluble. It says here also that all nitrates, acetates, perchlorates, group 1A metal salts are soluble. And come to think of it, there's one acetate that is not soluble. I think that is silver acetate. So that's an error there. But apart from that, the reason why I'm referring to this table is because I can explain the reason why ammonium chloride is soluble. It says here, most chlorides, bromides, and iodides are soluble. There are certain exceptions, lead 2 plus, silver plus, and mercury 1, right? So basically, the ammonium chloride that I referred to earlier, I know that is soluble because of what is stated right here. So you might find this table useful for making those kind of predictions, which is helpful when it comes to answering those questions. So going back to this here, as I said before, I knew that ammonium chloride is soluble in water, and therefore I know that it's going to undergo complete dissociation like this, right? And because of that, whatever the molarity of the ammonium chloride that you start off with, the amount of, or the molarity of the chloride will be the same. So therefore, when I'm setting up my ice table, first thing I need to ask myself is, how does ammonium react with water? And this is the equation right here. Because the original molarity of ammonium chloride is 0.42, that means that this is 0.42, and that means that the initial concentration of ammonium is 0.42. In the ice table, you're going to have 0 and 0 for the ammonia and the hydronium ion. The change here is going to be minus x, this is going to be plus x, and so on. So down here, you're going to have 0.42 minus x, you're going to have x here, and then you're going to set up your ice table, your equilibrium expression. Ka is equal to the concentration of NH3 times the concentration of H0 plus, divided by the concentration of NH4 plus. And again, you will not see the Ka for NH4 plus, but you will see the Kb for the ammonia, which is a base. So that's why we do this again. And it turns out that the Kb for ammonia is also 1.8 times 10 to the minus 5. So that means that the Ka for the ammonium will work out to be 5.6 times 10 to the minus 10, resulting from dividing the 1.00 times 10 to the minus 14 by the 1.8 times 10 to the minus 5. So as a result of that, we're going to end up with this expression here. You're going to end up with this expression here. Again, we're going to make an assumption that x is so small that 0.42 minus x is approximately 0.42. So that simplifies this equation. So when we solve for x, it turns out that x is equal to 1.5 times 10 to the minus 5. And then we, as always, must determine the percent dissociation, which is, in this case, equal to 1.5 times 10 to the minus 5 divided by the initial concentration of the ammonium, which is 0.42, which is 0.42, times 100%, and that gives you 3.6 times 10 to the minus 3%, which is obviously less than 5%. So therefore, we can go ahead and say that the concentration of the hydronium in this solution is 1.5 times 10 to the minus 5. And therefore, we can find a pH directly from that. And that's how we get a pH. pH is equal to 4.82. All right? So that's basically how that is done. So I hope that answers your question. Okay, let me deal with her first. Yes, ma'am.
Can we go back to the previous question?
The previous question. Right here?
Yeah. So, when making the chemical formula up there,
Here?
yeah, up there, because you said that the equation, like the acetic acid doesn't matter, like putting it together. So how would you know OH minus is a product?
Because the A minus is acting as a base. And what the base does is that it will remove a hydrogen ion from the water. So you're going to have an H plus transferred to the A minus. The result of that is that this becomes HA. And when the H plus leaves the water, it leaves behind the hydroxide ion.
So in general, is that how weak acids would act in this scenario?
And it's a weak base.
So
Right, it's a base.
it's a weak
Right,
base.
so basically, according to Bronsted, Bronsted basically says that a base is a substance that accepts protons, and acid is a substance which donates protons, right? In this case, the A minus is acting as a base, so it accepts protons from the water molecule and therefore produces the hydroxide ion as a result. So that's how you know that this is produced. All right. And another thing I want to say too, I remember saying it to a student, actually in class right here. When you're doing these problems, right? I could tell, for example, that the answer for the pH, which is what the question is asking for, the pH will be greater than 7 because of this reaction right here. It produces hydroxide ions, which means that the resulting solution is going to be basic. So because the solution is going to be basic, I know that the pH is going to be above 7, right? And we go through all the steps and you see here that the pH is, above 7, 9.15, all right?
So is the A minus representing the CH3
Right, CH3COO,
Na as well?
no,
Well, because Na dissociates.
right. So what is left after the Na leaves would be the CH3COO minus, which is the A minus,
Okay,
all right?
okay, yeah, it makes sense.
All right? Yes, sir.
Are we gonna have any problems on the finals, where the dissociation is over 5%?
Well, I haven't created the final yet, so I can't tell you. But it's possible. So if the percent dissociation is over 5%, then you know what to do. You'd have to go back to this right here and solve for X using the quadratic formula, which is the reason why I told you guys to make sure that you program your calculators to do just that, right? So after you get this in the form of a quadratic equation, then you plug in your A, B, and C values, and you're going to get 2 values. And usually you're going to get 2 values. In some cases, one will be negative and one will be positive, right? And we all know what to do with that, right? You ignore the negative because you cannot have negative concentrations, right? In some cases, you might have 2 values that are positive. So the question now becomes which one you're going to use, right? And the answer would lie in this part of the equation right here, right? Whatever the X value that you get, right? If you get 2 values, you're going to use the one that is less than 0.36 in this case, right? Because again, you cannot have a negative concentration, right? So if you have to, unfortunately, if you have to go through the longer route where the assumption is not valid and you solve for X and you get 2 values of X, which are both positive, then you have to look at what X is subtracted from, right? And if X is greater than 0.36, then you cannot use that value of X. You have to use the other value of X where X is lower than 0.36 or whatever this number is, right? Because this must be positive. It cannot be negative. All right? Okay, any other questions? Yes, ma'am. Oh, let me deal with the question here first and then Ms. Head, I'll answer your questions after. Yes, ma'am.
So that equation that's up there, would that be a buffer?
No,
So it has to be like the acid on the other side?
right. You have to have a significant amount of HA on this side here in order to make it a buffer, right? So for example, and usually a buffer is not created this way. You don't take A minus and add it to water to create a buffer. What you have to do is take A minus, a certain amount of A minus, a certain amount of HA, and mix them together. And that would be your buffer. All right? So, a buffer would be something like a 0.5 molar solution of acetic acid and a 0.4 molar solution of sodium acetate together in the same container, right? And then in that case, you don't have to go through ice tables. You just simply use pH is equal to pKa plus log of concentration of A minus over the concentration of HA, right? So basically, you just put the numbers in for those terms, and that's it. You get your pH. All right? Okay, Miss Head, you got a question?
Yes. So you said like when you're writing your equation, like Na and then that equals A minus plus Na, right? So like you said that CH3COO is just A minus. Is that what you said?
Yes.
Sorry about that. How did you know it was A minus? Like, why would it be a base, not an acid?
Because the salt, because A minus, okay, since we're talking about acetic acid, or the acetate ion, the CH3COO minus, let me do it this way. Let me clear this here. The main reason why you know it's a base is that it has a negative charge, but that's not the only reason. This is what happens. I'm going to write out the full formula. CH3 COO Na, right? When that dissociates, right, it forms CH3 COO minus plus Na plus, right? Now, when it comes to a salt, right? A salt usually has a positive part and a negative part. The positive part would be the cation and the negative part would be the anion, right? Now, the cation is potentially acidic. And I say potentially because not all of them are strongly acidic. In fact, this is so weak an acid that it doesn't have any effect on water when it's dissolved in water. And then the other part would be basic, right? Now, we know that it's basic because this here is the conjugate base of an acid, and the acid would be CH3COOH, right? So this is acidic, and the CH3COO minus is a conjugate base, so therefore it's basic. So that's why we know that this is basic and therefore will react with water. So I use the abbreviation A minus to represent the acetate ion, but basically, because it's basic, it's now going to take a proton from the water to form the products that you see over here on the right side of that equation, right? So to answer your question, basically, we know that this is basic primarily because it is negatively charged, and we know that it is formed from something that's acidic, right? When an acid loses a proton, whatever remains is going to be basic, all right? And the strength of the base that is formed is dependent on the strength of the acid, because as we learned earlier, the stronger the acid, the weaker the conjugate base, and vice versa, right? If you remember this equation here, Kw is equal to Ka times Kb, right? Ka is the dissociation constant of the acid. Kb is the dissociation constant of the conjugate base. And basically, when they multiply, you're going to get a constant value, right? So what does that mean? That means that the higher the Ka value for the acid, the lower would be the Kb value for the conjugate base, and vice versa, right? There's an inverse relationship between the strength of the acid and the strength of the conjugate base, all right? Okay, so I hope I've answered your question, Miss Head.
Yes, thank you.
All right. Okay, any other questions? Any other questions?
Professor,
Yes, that's Mr. Medina. Yes, sir.
could we go back to assignment number 1 and do question 7?
Assignment number 1. Let me clear this here. Okay, what question?
Question number 7.
Number 7. Okay, what is the boiling point of a 2.4 m aqueous solution of glucose? And it gives you the boiling point of pure water as 100 degrees, right? So the equation that you'll be using in this case, as soon as I can
Oh,
get back.
Professor.
Yeah.
Sorry, my mistake. I meant question 7 from assignment 2.
Oh, assignment 2. Okay,
Yeah,
so,
yeah.
all right. So let me go here. Assignment 2. Okay, let's see here. Question number 7.
Yes, sir.
Okay, question number 7 says calculate the activation energy for the decomposition reaction of, and it gives you the equation. And it says, given that the rate constant at 300 degrees Celsius is 5.7 times 10 to the minus 1, and at 230 degrees, it's 2.7 times 10 to the minus 2. All right, so the equation that you're going to use for this here, there are 2 forms of the equation. Which one would be the most useful? I think the one that is most useful is K is equal to A e to the minus EA over RT, right? Now, here's the thing. You're given two temperatures and you're given two values for the rate constants, right? So basically what's going to happen is that, okay, what we can do here is designate this one to be K1 and the corresponding temperature is T1. Now, the temperature has to be expressed in Kelvin. So we have to add 273 to this. So that becomes 573 Kelvin. And then we do the same thing here. So, but this time I'm going to call this T2. So 230 plus 573 gives 803 Kelvin, right? And this here I'm going to call K2, all right? Now, basically, for K1, that would be equal to A e to the minus EA over RT1. And for K2, that would be equal to A e to the minus EA. Oh, you know what? Hold on. We're trying to find the activation energy. So, okay, I won't use this form. It just occurred to me. The form I would use, there are two, let me just say this, there are different ways of expressing this relationship. This is one way. Another way would be ln K is equal to ln A minus EA over R times 1 over T, right? So that's another way of expressing this. Two different ways of expressing the same thing. What we're trying to find is this, right? So this is what I'm going to do. ln K1 is equal to ln A minus EA over R times 1 over T1. And then ln K2 is going to be equal to ln A minus EA over R times 1 over T2. Now, if I were to subtract this from this is what I'm going to end up with. ln K1 over ln K2 would be, and these two will cancel out each other, would be equal to minus EA over R times 1 over T1 minus 1 over T2. And then I would rearrange this to solve for EA because that's what the question is asking for. So EA would be equal to R times ln K1 over K2, all divided by 1 over T1 minus 1 over T2. And then it's all a matter of putting the numbers in. So I'm going to need more space. Let me just erase what's up here. So I'm going to end up now with EA is equal to R, which is 8.31 joules per mole Kelvin, times ln K1. So K1 is equal to 5.7 times 10 to the minus 1, m to the minus 1, s to the minus 1, divided by K2, which is 2.7 times 10 to the minus 2, m to the minus 1, s to the minus 1. And then all of that will be divided by 1 over T1. T1 is 573 Kelvin minus T2, which is 1 over 803 Kelvin. And that should give us our final answer. Let me erase this here. So what I'm going to do is I'm going to do this piecemeal, in a piecemeal fashion. I'm going to work out what's within the parentheses there. So 5.7 times 10 to the minus 1 divided by 2.7 times 10 to the minus 2. And according to my calculation, let me do this again just to make sure. 5.7 times 10 to the minus 1 divided by 2.7 times 10 to the minus 2. Okay, so this part works out to be ln 21. And I'm still going to have 8.31 joules per mole Kelvin. And down here now, I'm going to work out what's down here. So this would be 573, and then I find 1 over that, minus 803, and then do 1 over that. So according to my calculation, this part here works out to be equal to how many sig figs? Hold on.
I think T2 is supposed to be 503.
Yeah, thank you. So this should be 503. Okay, so this should be 503 down here. Thank you, Miss. Got your name. Anyway. So Miss Medina. Okay, so let me work on what's below. So 1 divided by 573 minus 503 . Okay, so I got rounded off to 3 sig figs. I got 1.99 times 10 to the minus 3. Okay, so now we have to just work out everything here. So 21 natural log times 8.31 divided by 1.99 times 10 to the minus 3. And that should not be negative. Let me do this again. Okay. So rounded off to 3 sig figs, that's going to be 1.27 times 10 to the 4. And the units here would be joules. This would be Kelvin to the minus 1. So this is going to cancel out with this. So you're going to bet 1.27 times 10 to the 4 joules per mole. And that's how that is done. All right. Okay, so I hope that answers your question, Mr. Medina.
On the assignment, the answer was a little bit different.
What was the answer in the assignment?
It's 1.04 times 10 to the 5.
Okay, let me check this again. We got 1.27 times 10 to the minus 10 to the 4. Let me check the bottom part here. Okay, I think I have discovered where I needed error here. Let me do this one more time. 573 minus 513. Okay. There should be a minus sign here. And this part here actually works out to be equal to minus 2.43 times 10 to the minus 4. Let's see if this changes things a bit. Well, it will change it. Let's see if that gets the answer that I had originally. So the actual answer is 1.04. times 10 to the 5. And this will be joules per mole Kelvin. And I realized the mistake I made. I did not do, when I was putting the numbers in the calculator, I neglected that. So that makes a difference right there. Okay. Okay, any other questions about this or? Oh, yes.
Professor. Why is there a negative sign next to 8.3 joules?
Because
Kelvin?
there should be a negative sign here in the form
Okay,
of,
the equation.
yeah, which I apparently skipped when I derived this equation right here. There should be a negative sign here.
Okay, thank you.
Okay, any other questions?
On the final exam.
On the final exam, okay, let me clear this. Which one?
8B.
8B. Eight B, okay. Okay, so this one is a carbon dating type problem. It says that it gives you the half-life and it gives you the mass of it gives you the mass of the carbon-14 material. So the question is asking how many half-lives has this sample been through, right? So basically, let me see here, hold on. Oh, I skipped this part. Only 15 grams remain. So you're starting off with 240 grams and you end up with only 15 grams remaining, right? There are a couple of approaches you can take, right? The approach that I showed here, which is more of a visual type of thing, is that I showed what happens when you reduce the original mass of the sample by half for each half-life, right? So you start from 240 to 120, that's one half-life. From 120 to 60, that's another half-life. And so on and so forth until you get to 15. So therefore, to get from 240 to 15 grams, you're going to have to pass through 1, 2, 3, 4 half-lives. And that's basically how you get that, all right? There's another way you could do this. There's a formula which I don't remember covering in class, but there's a formula which is M is equal to M0 over half raised to N, where N is equal to the number of half-lives. Right? So basically you have to solve for N. So basically you'd have to do like half to the N is equal to M over M0. And M over M0, M would be 15 grams. M0 would be the initial mass, which is 240 grams. So 15 divided by 240. Which is equal to 0.0625, which is the same thing as 1 over 16, right? So basically, you can deduce that half raised to the n is equal to 1 over 16, which means that n would be equal to 4. So that's another way of doing it, right? So the number of half-lives will be 4 as you go from 240 grams originally to only 15 grams, all right? Okay, any questions about this? Any questions? Any questions? So, like I said, I don't think I gave you this formula, but you can use this formula in those type of calculations, all right? let me clear this and scroll down to see what's below. Okay, what's the age of the log, right? So basically, we'll be using this equation right here. We know what M is, we know what M0 is. We don't know what lambda is, but we know what the half-life is. So lambda will be equal to ln2 over the half-life, and that's equal to 1.21 times 10 to the minus 4. So basically, we have everything now that we can plug into this equation to find t. We can rearrange this to get t is equal to minus 1 over lambda is equal to times ln m over m0, and then we put the numbers in, right? And that's it. We put m, 15 grams, m0 is 240 grams, lambda is 1.21 times 10 to the minus 4, years to the minus 1, and we do the computation and we get that result. And in fact, there's a much easier way of doing this. All we have to do is multiply the half-life by 4, because we know that to go from 240 grams to 15 grams, it takes 4 half-lives, right? And we already know what the half-life is. The question gave us the half-life, which is 5730. So that's even an easier way of doing it. So you should get the same result. So 4 times 5730 gives the same result, right? 2.29 times 10 to the 4. So more than one way of doing the same thing, all right? Oh, this one here, binding energy. In fact, I think this one is one that an exact problem that you're given in your assignment. They're asking for you to calculate the binding energy, right? And if you remember, I said that the binding energy is basically the difference between the sum of the masses of the particles in the nucleus minus the mass of the nucleus itself times c squared, right? So you need to find the mass defect, right? That's what the difference between the mass of the sum of the particles minus the mass of the nucleus itself. So that's how we do this here. You have to keep in mind, right, the composition of the nucleus, right? So for example, in the case of carbon-12, they gave you carbon-12, which means that the mass number is 12 and the atomic number is 6. So that tells you that the number of protons is 6 and the number of neutrons is also 6, right? So basically, to find delta M, we take 6 times the mass of the protons, add that to 6 times the mass of the neutrons, and then that sum, you're going to subtract from that the mass of the carbon-12 nucleus. That gives you delta M, which is the mass defect. So this is the mass defect right here, right? We have to convert that to kilograms in order to use the next equation. So 1 AMU is equal to 1.66 times 10 to the minus 24 grams, and we convert that grams to kilograms. This here is available in the table, right? So the table gives you the relationship between the atomic mass unit and the gram unit, right? So that's where we get this from. So we do that calculation, we end up with the mass being equal to 1.642 times 10 to the minus 28 kilograms, and then we multiply that mass in kilograms by the speed of light squared, and that gives you the binding energy, which is 1.48 times 10 to the minus 11, all right? So that's basically how that is done. And then, oh, and that's it. Okay, so that's it basically for that question. All right? Okay, any other questions?
Can we do 6B?
I'm sorry?
Can we do 6B from the same thing?
Same paper? Okay, 6B. B, okay. It says using the data in the tables provided, calculate the standard entropy changes. Oh, okay. So
Oh,
this is
no,
for,
sorry. It's
Sorry?
actually it's on page 12. I think there's 2 B's for this one actually.
okay, hold on. Page 12. Oh, you mean this one right here?
Yes, I forgot how to do these.
Okay, so entropy. Key thing you need to remember when it comes to entropy. By definition, entropy is a measure of the degree of disorder in a system, right? So the greater the level of disorder, the greater would be the entropy of the system, right? So if you remember, we said, for example, that if you take a substance and look at it in terms of its different states, solid, liquid, and gas, right? we know that the gas would have a greater entropy compared to liquids, which in turn would have a greater entropy compared to solids, right? Because the gas is more disordered than the liquid is more disordered than the solid, right? Or if you have a substance which dissolves in water, let's say sodium chloride dissolves in water, say starting with solid sodium chloride, you're going to end up with sodium chloride ions floating around in a solution. The ions floating around in the solution would have a greater entropy compared to the solid itself, right? So these are the things you have to look at in order to make predictions as to whether or not an entropy change will be positive or negative. So like in the case of this first reaction here, we have a liquid coming together with a gas to form a solid, right? So that corresponds to a decrease in the entropy, right? Because the entropy on this side here would be lower compared to the entropy on the reactant side. So therefore, the entropy change here would be negative, all right? In the case of 2, you're starting with a solid on the left side and you're ending up with a liquid and gas on the right side. So that tells you that the right side has more entropy compared to the left side. So therefore, the change in entropy in that particular case would be positive. And then in this case here, all we have in this case is 2 hydrogen atoms reacting to form, a molecule of hydrogen reacting to form 2 hydrogen atoms, right? So in this case here, you have basically 2 moles of gas on this side compared to 1 mole of gas on this side. So therefore, the entropy increases. So therefore, delta S is positive. And then in this particular case, you have a solid and a gas coming together to form a solid, right? So therefore, you have greater entropy on the left side compared to the right side. So therefore, in this case, the entropy decreases or delta S is negative. And then this one is easy because you're going from a gas to a liquid. So therefore, the entropy on the left side is greater than the entropy on the right side. So therefore, delta S would be negative in that case. That's pretty much it. All
Okay.
right.
And I think on the test yesterday we had a problem like this, but there was like some of the ones and they had like aqueous from them. So like what would you do
So-
there?
So if aqueous, that means that aqueous is usually has high entropy. Aqueous is almost the same as liquid. The aqueous state is almost the same as liquid state when it comes to entropy, right? So if you're going from solid to liquid, that corresponds to a delta S positive,
Okay, thank you.
right? Okay, any other questions?
Professor,
Yes, sir.
for number 4 right there, the H2 to the 2H, why was it a positive?
Because you're producing more moles of gas as you go from left to right.
Oh, okay. But don't they have the same since they're both 2?
No, because this is 1 mole of H2. This is 2
Mhm.
moles of H.
Okay. Okay.
So basically, you're looking at the coefficient in order to establish the change in entropy or the change in disorder, right? So this is more disordered compared to H2. So therefore, delta H will be positive in that case.
Also on page 11 of this
assignment?
yeah, could we do letter D?
Okay, so in the case of D, and actually D is very similar to the question that I gave you in the test that I just gave you. In this case, you're adding sodium fluoride to a solution that is 0.010 m lead 2 plus and actually this is more complicated actually. 0.010 m calcium 2 plus, right? So the question is asking at what concentration of the let me see here. And admittedly, this question should read, let me add this here. At what concentration of F minus, right, will a precipitate begin to form, right? So basically, the first thing you would do is consult the table and you look up the Ksp value for the possible products of that reaction. One of them would be lead 2 fluoride and the other one would be calcium fluoride, right? So you go to the table and these are the numbers that you're going to see, right? So basically, because the formulas are pretty much similar, where you have 1 unit of the metal to 2 units of the fluoride, we can simply compare these two to see which one will precipitate first. The one with the lower KSP value will be the one that will precipitate first. So that would be the calcium fluoride, because its value is 3.45 times 10 to the minus 11. Meanwhile, the lead-2 fluoride, its KSP value is 3.3 times 10 to the minus 8, right? So that's what I stated there. The calcium fluoride will precipitate first. So basically, we're going to use the KSP for the calcium fluoride to determine the concentration of the fluoride. Now, of course, and I skipped a step here, based on the expression for KSP, which is this, concentration of Ca2 plus times the concentration of F minus squared, right? Basically, what I did was rearrange this to get an expression for the concentration of F minus. That would be KSP divided by the calcium ion concentration, and then you find the square root of all of that. And then you put the numbers in, right? So we put the KSP value here, we put the concentration of calcium, which is given here, down here, and that would give us what the question is asking for, which is the concentration of F minus that is required to precipitate, or which will require to form a precipitate, all right? And that's basically how that is done. Okay? All right, any other questions? Any questions? Yes, sir.
This is related to this, but there's a curve at the end of the class.
Yeah, usually what I would do is at the end of the semester, after putting all the scores in, I'll look at who gets the highest and curve according to that. So if the highest after everything is done, if the highest is like 90%, then everybody's score total will be curved 10%. Right? So if you got an 80, it will be bumped up to a 90 and so on and so forth. So it all depends on who set the highest score. Okay, yes, ma'am.
Minus, how do we know it's squared?
Well, because, good question, because this is the dissociation. Yeah. Okay, any other questions? Any other questions?
Professor,
Yes, ma'am.
so I have a question, but it was about yesterday's test.
Okay.
It was like the very last question on the test, but I don't really remember it, but is it okay if we go over that one?
Well, I don't have it here, unfortunately.
Okay.
What was the last question? I don't remember what the last question was.
The last question was similar to the one we just practiced on right now.
Oh, okay. So if I remember correctly, the last question
It
based
just
on
wasn't as complex as this
right,
one.
it wasn't as complex as this one. I think the question was asking what would be the concentration. What would be the concentration of the iodide ion added? Right. It's very similar to this, excepting that we didn't have to concern ourselves. We didn't have to compare two KSP values, right? We only needed one, right? So basically it's the same thing. Whatever the KSP value was, you'd have to look that up and then you set it up according to this. I don't remember exactly what the compound, what was it? Was it lead-2 iodide? Right, so if I remember correctly, let me clear this here. It was PbI2, right, which will dissociate to form Pb2 plus I minus squared, or 2I minus, right? So KSP in this case would be equal to the concentration of Pb2 plus times the concentration of I minus squared. And basically you're asked to determine the concentration of I minus. That would be equal to KSP over the concentration of Pb2 plus, and then we find the square root of that. So basically, and I think the question gave you the concentration of Pb2 plus, and you'd have to look up the KSP value in the tables. You just plug those numbers in, find the square root, and that would give you what the question is asking for.
Okay, I see. Thank you.
All right? So I hope that answers your question, Ms. Head.
Yes, thank you.
All right. Okay, any other questions? Any other questions? Any other problems?
On 17, Professor, could we do letter B?
On page 17?
Yes.
All right, hold on 1 minute. Let me clear this. Okay, on page 17. Oh, wait a minute, 17. Oh, this one?
It's the one right after that, letter B.
Oh, this one, okay.
Yeah.
So it gives you the half reactions. So you notice I wrote the standard EMF values here because you'd have to look those up, right? So the question is asking, whoops, what did I do? Okay, so the question is asking, predict whether nitrate ions will oxidize Mn2 plus to MnO4 minus under standard state conditions, right? So these are the two equations given. I looked up the EMF values, standard, and I wrote them down here and here, right? So basically, if you remember, when they're adding two equations like this with their corresponding EMF values, one would have to be reduction, the other one would have to be oxidation, right? How do you determine which is which? Well, remember we said that the higher the EMF value, the more likely the reaction is going to occur as written, right? Now, in this particular case, what the question is asking is for you to predict whether the nitrate ions will oxidize the manganese 2 plus to MnO4. So what I did was that I kept this as it is, even though it has a lower value, right? Because I want to see if the nitrate ion will have that effect on the permanganate ion. And then what I did was I turned this equation around, right? Which means that I have to change the sign here. So that's what I did right here, okay? And then I add these two equations together. But of course, in adding these two equations together, I have to make sure that the number of electrons gained here must be equal to the number of electrons lost. So what do? We multiply this equation by 5, and we multiply this equation by 3, and we end up with these two equations here and here. And again, let me just say this. I remember stressing this earlier, and I'm going to stress this again. Whenever you're multiplying any equation, any half equation by any number, the EMF values are not affected. All right? That's very important for you to remember. A common error that students tend to make sometimes is that they multiply the EMF value based on the numbers that they multiply the equations associated with them by, right? You do that for enthalpy, you do that for delta G, you do that for entropy, but you do not do that for the standard EMF values. The standard EMF values remain the same. So that's why you see that these numbers remain the same right here. And then what I did was add these two equations together and cancel out what should be canceled out, which would be the 15 electrons here and here. 20 H plus will cancel out here with the 20 H plus here leaving behind 4. And then the 10 water molecules will cancel out 10 of the 12, leaving behind 2 here. So this would be the net reaction. And to get the net EMF value, I add this 0.96 to the minus 1.51, and I end up with minus 0.55 volts, right? So here we have the equation for the oxidation of the manganese 2 plus by the nitrate. Remember, the question is asking for you to predict whether the nitrate will oxidize the manganese 2 plus, right? But because the EMF here is negative, what does that mean? It means that that reaction will not be spontaneous, right? So therefore, the answer is that the reaction will not occur. In other words, the nitrate ion will not oxidize the manganese 2 plus, right? The reverse reaction is more likely to occur where the permanganate will oxidize the NO to form these two products, all right? So that's basically how that problem is done. All right? Any
Professor,
Yes, sir.
So why did we flip the second equation, the Mn4H2O?
Because you want to, because, okay, you're talking about this equation right here?
Yes, yeah.
Okay, because it's a redox reaction, right? You can't have one reaction where electrons are being used and another reaction where the electrons are being used. Remember, in a redox reaction, electrons are transferred from something to something, right? So one reaction, one half reaction must be an oxidation reaction, right? And the other half reaction must be a reduction half reaction. So therefore, we do not flip this right here because we need electrons on this side to cancel out with the electrons on the other side.
So can we not would we not be able to flip the first reaction then
Yeah,
instead?
you could do that. In fact, that's another way you could do. You could flip the first equation here, but that means you'd have to flip the other equation.
Okay.
You see what I'm
And
saying?
then yes, yes. And the EMF value, if it's negative, then it's you said it wasn't spontaneous.
Right. So, right, if you get to this stage and you get a negative EMF value, then that means that the reaction is not spontaneous as it is written. The reverse reaction would be spontaneous.
Mm.
All right?
I thought it was the if it's positive, so if it's positive, it's not spontaneous, right?
No, positive is spontaneous.
Positive is spontaneous?
Yes. If I'm talking at the end here. I'm not talking about each of these here. I'm talking for the final equation here, right?
Okay.
If the standard EMF value is positive, what that means is that that reaction, as it is written, is spontaneous.
Okay, so then is it for only for delta G? If delta G is
Okay,
negative,
so that's something
then
different now. Delta G,
okay.
right? Okay, so I think you're probably mixing up delta G and the EMF. If
Yes.
delta G is negative, then the reaction is spontaneous.
Yeah, right. Okay. So it's just the
Delta G is
opposite for
positive,
EMF.
then the reaction is not spontaneous. And remember, there's a relationship between delta G standard and the standard EMF, and that is delta G standard is equal to minus NFE standard. And because of this negative sign, you see that kind of inverse relationship between delta G standard and E minor and E standard, right? Because if this is positive, that means that delta G is negative, which means that the reaction is spontaneous. Oops. All right. On the other hand, if E0 is negative, then delta G is positive, which means that the reaction is non-spontaneous. All right?
Okay, I see now.
Mhm. Okay, any other questions?
The question on the last page.
On the last page, okay, let me clear this. Okay, I think we did this one. Where did we do this? I think this was in the assignment, if I'm not mistaken. Anyway, let's do this one. Okay, so the question is asking, it gives you the KSP for silver bromide, so you don't have to look that up. And then it says, calculate the molar solubility of silver bromide in water. Oh, I remember this question because I neglected to separate the different parts. So this is the A part. And this is the B part. And this is the C part. Okay, so the first part, the A part, is asking for the molar solubility of silver bromide in water. And apparently I did not answer that down here. So let's check something here. Yeah, I did not answer that down here. I don't know why. Anyway, Let's do that now. So, I should be able to squeeze it in out top here. So silver bromide dissociates the form Ag plus Br minus, right? So initially, we had none of these two here. Change here is going to be plus S if S is a solubility. And at equilibrium, you're going to have S and S, right? So Ksp is going to be equal to S squared. This implies that S will be equal to the square root of Ksp, which will be equal to the square root of 5.35 times 10 to the minus 13. So that would be equal to 5.35 times 10 to the minus 13. And according to my calculation, this works out to be equal to 7.31 times 10 to the minus 7 M, all right? So that's the molar solubility in pure water, all right? Then the question says, silver forms a complex with ammonia, which is this right here. The Kf for this complex is 1.69 times 10 to the 7. So the question is now asking for you to calculate the molar solubility of silver bromide in 1.5 M ammonia. And then, okay, so that's the B part. So let me clear this here. Scroll down. So there are two reactions that will be taking place, right? One would be the one that we saw before, which is the dissociation of silver bromide to form silver ions and bromide ions. And the Ksp for that is given. And then the silver ions that is produced in the first step will combine with ammonia according to this equation. Now, we could figure out this equation because the question gave us the formula for the complex, AgNH32. So that means that there's a 2 for the coefficient for the ammonia here that would be included when you're writing down this equation. You're also given the Kf for this equation, which is 1.69 times 10 to the 7, which is this right here. So basically, we can write down an overall equation by adding these two. And again, as always, when you're adding two or more equations, you cancel out those items that are common to both sides. In this case, that would mean that you'd cancel out the silver ions here and the silver ions here, right? And then you just write down what is left. To get the Kc for this overall equation, if you remember, when you're adding two or more equations, to get the Kc for the final equation or the net equation, you multiply the Kc or the K, whatever, it doesn't matter, of the other equation that you're adding to each other. So in this case here, you'll be multiplying the 5.35 times 10 to the minus 13 by the 1.69 times 10 to the 7, and that gives you the Kc, which is 9.04 times 10 to the minus 6, right? Then we set up our ice table, right? So we're going to start off with the 1.50 M ammonia. And again, we're going to say let X represent the solubility of silver bromide. So for every 1 mole of silver bromide reacting, the change in the ammonia concentration would be twice that value. So if X is the solubility, then the change in the concentration of ammonia would be minus 2X. And over here, the change in the concentration of the complex, and I made a slight error here. Let me correct that so that this here should be, it should have a 2 here. All right. So as far as the silver complex is concerned and the bromide, those changes would be X and X as well. And then at equilibrium, you're going to end up with these terms right here. 1.50 minus 2X for the ammonia and X here for the complex and for the bromide. And then we set up our equilibrium expression, Kc, that will be equal to the concentration of the complex times the concentration of the bromide. And I'm making the same mistake here again. This should be a 2 right here. All divided by the concentration of ammonia squared, right? And of course, the ammonia is squared here because we have the coefficient of 2 right here, all right? So we put the numbers in, the terms in, and we end up with this expression, X squared over 1.50 minus 2X is equal to 9.04 times 10 to the minus 6. And then what I did was find the square root of both sides. and I end up with this expression here, x over 1.50 minus 2x is equal to 3.01 times 10 to the minus 6. And then I solve for x, right? So again, we have to take some algebraic steps. I added, okay, let me clear this here just to show you stepwise how this is done. So what I would do is I would add 6.02 times 10 to the minus 3x to both sides, right? This will disappear, and I'm going to end up with x plus this. X plus this is basically going to be the same as x, even though I wrote out all the numbers here. When you put those numbers in a calculator, you're going to end up with 1.00602 times x. So this is almost 1, right? So if you rounded this off to 1, no problem. Ultimately, you're going to get x being equal to 4.52 times 10 to the minus 3 divided by that. And that will give you the concentration of the silver ions, which I think is what the question is asking for, or the solubility of silver bromide, I'm sorry. The solubility of silver bromide. So that would be the answer here, all right? And then I think the other part, the C part is asking for, let's go back up here. The C part is asking for, oh, the mass of silver bromide. So once we have the solubility, it's all a matter of, hold on. Multiplying the solubility by the volume, which has to be in liters, which is what I did right here. So the solubility that I calculated earlier, which is 4.49 times 10 to the minus 3 moles per liter, I multiply by 175 mils, which is the same thing as 0.175 liters. And we multiply that by the molar mass, because when you multiply the volume by the molarity, that gives you the moles, but the question is asking for the mass. So we have to multiply that value by the molar mass, and we end up with 0.148 grams as the amount that will dissolve in this solution. All right? So that's basically how that is done. Any other questions about this? Any other questions?
Professor,
Yes, sir.
could we go back to page 17 for question B, the one that we just went over?
Page 7,
Page 17.
17.
Yeah, question B. I had another question about.
Hold on. No, hold on, hold on. I'm not, you said question number what?
Letter B, the one with the half reactions.
Oh, this one. This one?
Yes,
Okay.
yes. So, you said I could also, instead of reversing the second equation, I could reverse the first one?
Yeah, but that will give you the reverse reaction. It will give you, when you go through all the steps and add them up, you're going to get this reaction in the reverse.
Right.
But
So,
you're going to end up with a positive 0.55 volts.
yeah, so if it was positive, then wouldn't the reaction occur?
Yes, but that's the reverse reaction. What we're concerned about is the manganese undergoing oxidation by the nitrate. Remember, the question is asking, predict whether the nitrate ions will oxidize the manganese, 2+. So that's why I made sure that the nitrate and the manganese are on the left side, because I want to see if that reaction will take place, if that reaction is going to be spontaneous. So that's why I kept the nitrate here, and that's why I flipped the other equation to get the manganese on the same side as the nitrate. You see
Okay,
what-
so then we would want to have the second equation reversed so then we could have the nitrate and the manganese on the same side.
Exactly. And then after you go through all the steps and find the EMF value, you're going to see what the sign of the EMF value is for the oxidation of the manganese by the nitrate. And we see that it's negative. So therefore, we know that that oxidation will not take place. We know that that oxidation is not spontaneous.
Okay, could we still answer this question if we had this final equation reversed and it was
Yeah, you
a
could,
positive?
right? You could say that, how would I put it? You could say that the reverse reaction is where the oxidation will take place, but because the reverse reaction is not spontaneous, then we know that the oxidation will not take place. So you have to add some, you have to add a statement to explain what your answer is.
Okay.
Right? But I decided to write it this way so that you can see directly that the nitrate will not oxidate. I'm sorry, what am I saying? Yes, the nitrate will not oxidize the manganese 2+. Right? Okay, any other questions? Any other questions? Or should I take it you're all ready? Ready to bust the name in this final exam?
Professor,
Yes, sir.
could we go to assignment number 1 and do question 9?
All right, hold on. Let me clear this here. Assignment number 1, I think I have it up here already. And you said question number what?
Question number 9.
Number 9. Oh, okay. So the question says an aqueous solution freezes at minus 6.51 degrees Celsius. What is its boiling point? Okay, so in this particular case, you'll be using two equations, which look similar, but they're different. So let me remind you of these two equations here. One of them is delta TB is equal to KB times M, right? And just to remind you, this is the elevation in boiling point, right? The other equation would be delta TF is equal to minus KF times M. And please do not forget the negative sign, right? Now, delta TF would be the freezing point depression, right? And the KB and KF value are constants, which are given in the table. In fact, let me see. If they're not given in the table, then I would have to provide it, but I'm quite sure it's provided in one of these pages. Which one is it? Okay, here they are. Okay, so this is KF for water, and this is KB for water, right? So those two values you're gonna need. In fact, let me write them down. here. So KF is equal to 1.86. And this would be degrees Celsius over M, and KB would be equal to 0.512 degrees Celsius over M. All right, so you're gonna need those values in order to answer this question. So let me go back to, okay. So the question is asking for the boiling point, all right? So in order for us to get the boiling point, we need delta TB, right? To get delta TB, we know what KB is already, but we need the molality. So how do we get the molality? Well, we have to come up with this equation here. And the question gave us the freezing point of the solution. We know what KF is, so we can find the molality. So what I'm going to do is say M is equal to minus delta TF over KF, right? So what is delta TF? Well, the delta TF would be the freezing point depression of the solution compared to water. That would be the final freezing point of the solution, which is minus 65.6.51 degrees Celsius, right? Minus the freezing point of water, which is 0.00 degrees Celsius. All of that divided by KF, which is 1.86 degrees Celsius over M. So let's see what that gives. So that the top part is basically 6.51 divided by 1.86. And according to my calculations, this works out to be equal to 3.50 M, right? So now that we have M, then we can use M over here, the same M value over here, to find delta TB. So delta TB would be equal to KB, which is 0.512 degrees Celsius over M, multiplied by 3.50 M. So let's see what that gives. That gives 3.5 times 5.12. And according to my calculation, this works out to be equal to 17. Let me do this again. 3.5 times 0.512. 1.8. I'm sorry. 1.80. No, I'm sorry. 1.79. My bad. 1.79 degrees Celsius, right? So delta TB is equal to that. Now, the question is not asking for delta TB, it's asking for the boiling point, right? The delta TB would be the boiling point of the solution minus the boiling point of the solvent, right? So TB, the boiling point of the solution, would be equal to delta TB plus the boiling point of the pure solvent. So the boiling point of the pure solvent, well, delta TB first is 1.79 degrees Celsius, plus the boiling point of the pure solvent, which is 100.00 degrees Celsius. So the final answer is going to be 101.79 degrees Celsius. And that's how that is done. Any questions about that? Any questions? Or any other questions?
Can we do number 11 on page 7 of this assignment?
Okay. Okay, number 11. Oh, this one has to do with osmotic pressure. So it gives you the mass of urea, it gives you the volume, and it gives you the temperature. So the equation you're going to use, and the question is asking, oh, that's easy. The question is asking for the osmotic pressure. So the equation you're going to use is I is equal to MRT. M is the molarity, R is the molar gas constant, T is the temperature, and pi is the osmotic pressure. So they did not give us the molarity, but they gave us the mass, they gave us the volume, and they gave us the formula, right? So we need the molar mass. So again, you know me, how lazy I am. I'm going to use the molar mass calculator. To find the molar mass of urea. And the formula for urea is NH2 and then 2 and then CO. I should get 2 here. And calculate. 60.06, right? So okay, so to find the molarity, to find this part here, we take the 2.02 grams divided by the molar mass, which is 60.06 grams per mole. And then whatever you get from that, you divide by the volume. The volume is 145 milliliters, so that's the same thing as 0.145 liters. And then I'm going to multiply all of that by R, which is 0.0821 liters atmospheres over mole Kelvin times the temperature. What's the temperature? 20 degrees, which is the same thing as 293 Kelvin. And that's it. So let's see, 2.02 divided by 60.06 divided by 0.145, and then I multiply by 0.0821, and then I multiply by 293. And according to my calculation, this works out to be equal to 5, how many sig figs? 3 sig figs, so 5.58. And the units here would be atmospheres, because the gram units will cancel out, the mole units will cancel out, the liters unit will cancel out, the Kelvin units will cancel out, so you're left with atmospheres as your final unit. All right?
What's the difference between the two values of R?
Okay, so and very important question you just asked, right? Because depending on the type of equation you're working with, you have to be careful about the choice of the R value you're going to use. One R value is one that you should be familiar with from your Chem 1. R is equal to 0.0821 liters atmospheres over mole Kelvin, right? But there's another value of R, which is 8.31 joules per mole Kelvin. They're both equal to each other, but you'll notice that in addition to the numbers being different, the units are different as well, right? So you have to be careful. I would say that a good rule of thumb for you to determine which of these you're going to use in a particular calculation is based on whether or not some energy unit is involved in your calculation, so that that can be taken care of in terms of cancellation. Or if you have atmospheres and liters involved, then you will use this value here. So it all depends, right? So like in this case here, because the question is asking for pressure, right? And because the question gave you volume, then I would use this value of R, because we have liters here and we have the unit for pressure, which is atmosphere, right? But there are other instances. Can't think of one right now, but there are other instances where you might have joules. Oh, good example of that would be the one that we just looked at, where we had K is equal to A e to the minus EA over RT, right? Remember that? Well, this is in joules, right? So therefore, the value of R that I would use is the one that contains the joule units. You see what I'm saying? So it all depends on the type of equation and the units that would be involved. All right? Okay, any other questions? Any other questions? In the 5 minutes we have left? Oh, by the way, I don't know if you guys saw the announcement I posted today. So, somebody was suggesting about having pizzas for the last day. So I was thinking that we could do that tomorrow. That's up to you guys, of course. But be prepared to chip in. I don't know how much would I require for you to chip in per person? Maybe 10, 5 or 10. $5? All right. I'll make sure order before and then you guys can send your contribution. And that include you guys too out there in Zoom, but you'd have to be here in person to partake. So I don't know if that would serve as some incentive for you to come here. But yeah, so we'll do that tomorrow for last day of review. Okay, any other question? Yeah, okay.
Is there any way you could post in Canvas, like, a head count of who's coming? That way we know how much pizza we need.
Oh, okay. Okay, so please indicate by, how should I do this? By email. Just send an email just to let me know how many of you are coming. Before tomorrow or by tomorrow. And we can get a head count. Okay, somebody's asking, when will we pay the $5? When you get here tomorrow. All right, yeah, just send me an email just saying whether or not you're coming tomorrow. Okay, any other questions in the 3 minutes we have left? Any other questions? If not, then that's pretty much it for today. So I'll see you guys tomorrow at 12. All right, take care.